This is number 3 non-calculator AP FRQ review on derivative graphs. So the graph of the continuous function g is the derivative of the function f, so we can really call this f prime. Function g is piecewise linear function, so we have all these lines here except for this last portion, which is a parabola 2x minus 4 squared from 3 to 6. If f of 1 is equal to 3, what is the value of f of negative 5? So anytime I'm looking for a location and I'm given another location, I can think of it as looking for position value. So anytime I'm looking for a position value, I like to think in terms of initial plus displacement. So f of b equals f of a plus the integral from a to b of f prime. So if I want to find f of negative 5, I can plug in, I want to start at f of 1, and then I got to bridge the gap from 1 to negative 5. Now whenever you want to follow this formula for initial plus displacement, make sure that you start off with your lower bound matching the same value as your initial, and then your upper bound matching the value of your final. Okay, that we need to do first. And then after you enter your initial lower and upper bound, if you realize that it's out of order, then you can flip the signs or flip the bounds. And if you flip the bounds, then you can change the sign. Okay. I think sometimes students want to just go ahead and put the smaller value below the upper value being the higher number without taking into account that it could force a change in sign. So I would always say start off with whatever your initial value is, then move to your final value, and you see there's a need for change, make that change, and then balance it out with changing that sign. So f of 1 minus the integral from negative 5 to 1, so f of 1 is going to be 3, and then the region from negative 5 to 1, it's going to be all this right here. Okay. So this is a rectangle here that has an area of 9, but it's below the x-axis, so negative 9. This here is a triangle, 1/2 base times height, which is negative 1/2 times 1 times 3, which will be 3/2, but it's below the x-axis, so I'll make it negative 3/2. And here, another 1/2 base times height, triangle, 1/2 1 times 2, which will give us 1, that's above the x-axis, so positive 1. So I'll put it all in place of the integral from negative 5 to 1. There's negative 9, there's negative 3/2, there's plus 1. Combine those together, and this results in negative 19 over 2. There's another negative out in front, so the two negatives becomes positive. So 3 plus 19 over 2 gives us 25 over 2. For part B, it says evaluate the definite integral from 1 to 6. So from 1 to 6, let's look at what the graph shows us here. So from 1 to 3, we see it's just going to be a horizontal line, which we can easily find the integral for. Just going to be 4, right? This area, that's this square here, 2 times 2. But then we move on to the curve, and to find the region under the curve, we have to rely on power rule, and we need a function to help us get through that. So maybe it'll help to split this up into two integral problems. We have one that we can just read from the graph, and the other one we're going to have to rely on expansion, power rule, and first theorem of calculus. So the integral from 1 to 3 is just going to be 4. We saw that that square region there, 2 times 2, width times height. And the integral from 3 to 6 is going to be under this curve, which is 2x minus 4 squared. We could expand this out, but I could also go through u substitution, make what's inside the parentheses be our u value. We find the derivative, cross multiply, replace dx and the x minus 4 with u and du. And once we have that set up, everything is set up and ready for power rule. So I apply power rule. U squared becomes u cubed over 3. I have my antiderivative. Replace the u back in terms of x. That way I can go back and use my bounds. So we don't want to plug in the 6 and 3 here, because the 6 and 3 are in terms of x, and we need to make sure that we don't have a mismatch in variables. Okay, so we apply power rule, replace the u back in terms of x. Now we can plug in the 6 and 3. So 6 gets plugged in first. 6 minus 4 is 2. 2 cubed is 8. Minus, plug in that 3. We get 3 minus 4, which is negative 1. So we get 16 over 3 plus 2 over 3, which is equal to 18 over 3, which is 6. So the results of the integral from 3 to 6 is equal to 6. 6 plus 4 is equal to 10. Part C, between negative 5 and 6, is there a point where the graph is both increasing and concave up? All right, so finding increasing and concave up means that we want to, first off, we're looking at the derivative graph. So increasing just means wherever the f graph or the f prime graph is above the x-axis. And we want concave up, so if we're looking at the derivative graph, it's wherever there's positive slope. So we're looking for regions where our derivative graph is above the x-axis and displaying positive slope. So we can say from 0 to 1, above the x-axis and positive slope, and also from 4 to 6, above the x-axis and positive slope. For part D, find x-coordinate of each point of inflection. So point of inflection off the derivative graph are the peaks and valleys. So we want to see where is our slope going to change from positive to negative or from negative to positive. So no relative max, relative mins up until 4, right? That's the only place where we're getting a distinct decrease followed by increase. We don't see any other places where there's decrease followed by increase or increase followed by decrease. So the only point of inflection is at x equals 4 because f prime changes from decreasing to increasing.